When you search for a new phone and tap a link, beneath the glass, your device instantly begins building a message. This message is an HTTP GET request. It's a strictly formatted block of text asking a server to send back a specific web page. To send it, the device routes this text packet out through port 80, the standard open channel for web traffic. Human-friendly names like shop.com mean nothing to the network hardware. Before the request leaves, the browser checks a domain name system, or DNS server. This acts like a directory, translating that text address into a machine-readable IP address, the exact physical destination for the request. This model illustrates the evolution of how those requests travel. Early versions of HTTP were strictly sequential. A browser asked for an image, waited for it to arrive, and then asked for the text. This single file line caused massive delays, known as head-of-line blocking. Modern connections solve this with HTTP2 multiplexing, shown here on the right, which bundles multiple requests and responses simultaneously over a single connection, drastically accelerating page loads. This parallel pipeline makes the modern web incredibly fast. But speed is only half of the equation. The architecture of this HTTP request relies on an open protocol, which lacks the built-in security required to safely handle the modern digital economy. The user proceeds to checkout and types in a credit card number. The browser now forms an HTTP POST request, a specific command used to submit data up to the server, rather than just asking for a page. This packet leaves the phone and enters the local network environment, perhaps a public Wi-Fi router at a coffee shop or an airport. It is no longer under the device's control. The internet is a web of interconnected hubs, meaning data does not travel in a straight private wire. It hops from node to node. At any of these junctions, someone with the right access can perform a man-in-the-middle attack, quietly recording the data as it flows past. This container illustrates the core vulnerability. Because plain HTTP does not encrypt data, the payload travels in clear, easily readable text. If an attacker intercepts this transparent box, they can instantly read every single digit of the credit card. HTTP was originally engineered in a laboratory for scientists to openly share research documents. It was never intended to hide information. Sending personal secrets through this system is like writing your password on the back of a postcard. To protect that data, the browser immediately shifts communication from the open port 80 to port 443. This is the designated channel for HTTPS. This diagram shows how HTTPS works. It doesn't replace the HTTP language at the application layer. Instead, it inserts a security layer right beneath it. This is Transport Layer Security, or TLS. It takes the standard HTTP conversation and wraps it in a protective shell. Before applying that shell, the client must solve a critical problem. It needs proof that the server on the other end is actually the legitimate store and not an attacker mimicking the website. To prove its identity, the server presents a digital certificate. This document is part of a certificate chain, where trusted third-party organizations, called certificate authorities, mathematically vouch for the server. When the browser verifies these signatures, it displays the familiar padlock icon. Without this verification step, a device could establish a perfectly encrypted connection with a disguised criminal. Establishing verified identity is the mandatory prerequisite for trust. Now the two devices must lock the data, but if they lock it with a single shared key, they have to send that key across the open network. If a man in the middle intercepts the key, the lock is useless. We can see the solution in this model of asymmetric encryption. The server issues a blue public key that can be shared with anyone. It can only lock the container. To unlock it, the receiver must use a mathematically linked, closely guarded red private key. While highly secure, asymmetric encryption requires complex mathematics. If we attempt to push thousands of data blocks through this mechanism, the system grinds to a halt. It is far too slow for continuous web browsing. Symmetric encryption uses a single key to both lock and unlock data. It is lightweight and incredibly fast, ideal for handling heavy web traffic. The client generates a fresh, temporary version of this, called a session key. To safely deliver this fast key, the client places the session key inside the heavy asymmetric container, locks it with the server's public key, and sends it across the network. Only the server's private key can open it. This process is the TLS handshake. By using slow encryption just once to safely share a fast key, the devices bridge the gap between security and speed, making encrypted global communication physically viable. With the session key safely established on both ends, the device encrypts the HTTP post request. It uses robust algorithms like AES and SHA-256 to scramble the credit card data into ciphertext. The packet leaves the device and travels back over the public Wi-Fi network, where the man in the middle is still quietly recording all passing traffic. Look at the packet now. Because it is wrapped in TLS encryption, the attacker can no longer look inside. When the scanner intercepts the payload, it captures nothing but scrambled, mathematically unbreakable static. The packet arrives safely at the destination server. Using its copy of the session key, the server decrypts the payload, processes the payment, and packages its reply, encrypting the response for the return trip. Inside that encrypted response is a standard HTTP status code. If the payment succeeds, the server replies with a 200 OK. If the page was missing, it would send a 404, or a 500 if the server itself crashed. By securing the entire round trip, HTTPS prevents eavesdropping and guarantees the data wasn't altered in transit. The request and the response arrive exactly as intended. The underlying mathematics of TLS are formidable, but we must ask how this system holds up against attackers in real-world deployments. This table outlines historical exploits against the protocol. While the core math remains sound, vulnerabilities like Poodle or Heartbleed arose from relying on outdated SSL versions, weak encryption algorithms, or flawed software implementations. This terminal output shows the results of an automated security scan. Engineers run tools like Test SSL against their own servers, deliberately searching for weaknesses, such as a reliance on outdated ciphers that expose the system to known attacks like Suite32 or Logjam. Maintaining an impenetrable shield requires constant vigilance. Network administrators must regularly update their systems to deprecate legacy SSL versions, strictly enforce modern cipher suites, and properly pad data to mask patterns from timing attacks. Look at this map of global traffic. The same encrypted handshake that protects a credit card now secures the streaming video you watch, the thermostats in your smart home, and the trillions of dollars moving through the global banking system. HTTP was originally built for academics to share open documents, not secrets. By wrapping that original language in cryptographic armor, engineers successfully adapted a research tool to carry the weight of global commerce.